All right, today we're going to talk about the moose in the road problem, which is really about reaction time and stopping distance. So imagine you're driving down a rural road at a constant speed of 13 meters per second, which is about 30 miles an hour, and a moose is in the road. You notice the moose and realize that you need to stop, but you can't just stop instantly. For one, you have to realize that there's a moose and you need to stop, and that signal has to go from your brain down through your nervous system and into your foot so that your foot will get off the gas pedal and go onto the brake. Then, while that's happening, you're still moving down the road because you're traveling at 30 miles an hour and your foot is still on the gas pedal until you react. Once you react, you're going to then put your foot on the brake and then stop. But while you're stopping, you're still moving down the road because you don't just stop instantly. The car slows down to a stop and it does that over a certain distance. So what we're going to do is we're going to figure out what that stopping distance is from the instant that you see the moose and realize you need to stop until you actually do stop. So first thing we're going to do is draw a VT graph of the motion of your car. So you click on the graph, click edit, and then we know that the speed is going to be constant while you're reacting. So constant speed looks like a horizontal line. You can change the color if you'd like. You can change the weight. And then we're going to slow to a stop. So we're going to go from that speed, that 13.5 meters per second, down to 0. You can hit save and close, and then your graph is done. Finish. There we go. All right, so next, we want to know how far did the car go down the road while you were reacting. So the distance that the car is traveling at a constant speed while you're reacting and moving your foot from the gas pedal to the brake pedal. In previous years, what we would do is have you do a lab where you'd figure out your reaction time of stopping. You may have done this lab in biology where a friend of yours would hold a meter stick, you would have your hand ready to grab it, drop the meter stick into your hand, you'd grab it, see how far it fell, use a magic formula, and figure out what your reaction time was. We now know that magic formula is time is equal to the square root of 2d over a, because that's one of our equations that we use to figure out time. Using your foot is a little bit different. The nervous signal has to travel a little bit further. So instead of going from your brain to your hand, it's going to go from your brain all the way to your foot. And what we would do is have students sit on a chair and have their foot up against the wall, pretending that that's a gas pedal, and then their friend would drop a meter stick, and then they'd move their foot over onto the meter stick to stop it like it was the brakes. What we find is that a typical reaction time using your foot is about 0.4 seconds, which is a little bit longer than about the 0.2 or 0.3 seconds that your hand would have, which makes sense because it's a longer distance that you need to have that signal transmit. So the upshot of that is that we know our car is traveling at 13.5 meters per second. And the time it's going to do that is our reaction time. And then that's how far we're going to be headed down the road. So we're looking for distance. So now we need an equation for distance. So if you find your equation sheet, and I like the second page because it separates everything out by what you're solving for. We've got d is equal to vt. Well, that's for constant speed, and that's what we've got. So we haven't been able to use this equation for a really long time, but that's so cool because that's a nice, easy equation. So we have d is equal to vt. We do our substitution, d is equal to 13.5 times 0.4. And now we need to multiply that. Whatever calculator it is that you use, that's what you should use. I like this kind the most, but I'm going to show you using that on Desmos. So we have 13.5 times 0.4. And what that gives you is 5.4. 5.4 meters is about 17 feet. So a meter is about 3 feet. It's a little bit longer. So if we have 5.5 meters, it's pretty close to 17 feet. So that's a pretty long time. So while your brain is going, a moose, and it's sending the signal to your foot, and your foot is still on the gas pedal, you're going down the road 17 feet if you're traveling at 30 miles an hour. So the next question, how far down the road do you go while you're stopping? So now we've reacted. So the reaction time is no longer part of this problem because you've already reacted. So we know that our V initial is going to be equal to 13.5 meters per second. We know that our V final is going to be equal to 0 because we're going to come to a stop. The other thing we know is this piece of information up here, that the National Highway Transportation Safety people say that your car can stop at a maximum rate of negative 10.6 meters per second squared. They have this awesome track where they take cars of all kinds and tires of all kinds and they slam on the brakes and they skid and then they wet the track down and then they skid some more and they take all kinds of measurements, and part of what they do that for is for safety stuff, to make sure that cars are safe to travel in. But part of the reason that they do that is to make a database that police can use when they're doing accident reconstructions. And what we find is that a car, your basic car, with good tires on a dry road can stop at negative 10.6 meters per second squared. So now we know our acceleration. And we are looking for the distance that we travel while we stop. To get a superscript, I use control period. And if you need to unsuperscript, you do the same thing. So control period gets it back to normal again. So now we need an equation for this. So if we go to our equation sheet, we can no longer use d equals vt because we have acceleration. So that does not work. D is equal to 1/2 at squared plus bit does not work because we don't have time. The time that we had before, that 0.4 seconds, was the reaction time, not the time of braking. And so the acceleration is only happening while your foot's on the brake. We don't know how long your foot is going to be on the brake for. So that equation doesn't work. So the only equation that's going to work for us is this one. D is equal to V final squared minus V initial squared all over 2a. So to type that in, we could do this. And so if you don't want to worry about equation editors and stuff like that, you can type it in kind of horizontally that way. Or you can cut and paste from the equation sheet, or you can use Equagio. So I'm also going to show you Equagio. So there we go. I really like the handwriting recognition one. I think that makes things easier. So we have D is equal to V final squared minus V initial squared. Over to A. And then if there's anything you need to fix, we can do that. So this one here needs to be an F. This needs to be an I. We can make those lowercase if we want to. And then we're going to go ahead and insert math. So now our substitution. So D is equal to V final is 0. So it's not the biggest number minus the smallest number. It's V final minus initial. And then divided by 2 times a negative 10.6. We need to put these as squares. Oops. And this is actually one of the places where Equatio is pretty cool because we can copy the equation that we just made and paste it here. And then we can edit math. So we can replace all of the stuff that we've got here with our answers, our substitution. So we've got 0 squared minus 13.5. I'm using the character above the 6 to get the squared. And then 2 times negative 10.6. And we can insert math. So that would be another way to do that substitution. So now we get into our calculator. So we've got 0. And then you don't really need to, whoops, move that. You don't really need the squared because 0 squared is going to be 0. But we'll put it in there. Then we have 13.5 squared, then divided by, and I needed parentheses there, so let's go back. The whole thing divided by, and then 2 times negative 10.6. And you can see our answer is 8.5966, etc. And we want to round that to 2 digits, so 8.6 meters. So the next thing, how far total did the car go down the road from the time that you saw the moose to the time the car actually stopped? So whenever you hear the word total in math class, you should think add. So our distance that we moved while reacting was 5.4 meters. Our distance that we moved while stopping was 8.6 meters. So if we add those two things together, we end up with a distance of 14 meters. That works out to about 45 feet. So from the time you go, a moose, to the time that you actually stop when you're traveling at 30 miles an hour is about 45 feet. That is a pretty long distance. Now, this whole thing was assuming that we were prepared for a moose. We were driving around and we were thinking, wow, there's going to be a moose any second now. I need to be vigilant. But most people probably don't drive like that. So the questions are actually asking about what would happen if you weren't driving perfectly. So in question 3, how would your reaction change if you were driving while distracted? So if your friend sends you a Snapchat and you pay attention to it, or you're fiddling with the radio, or you're taking a sip of a drink, what is that going to do to your reaction time? And then what will the change in reaction time do to your stopping distance and why? Question 4 is saying, now let's think about going at a faster speed. So maybe you're traveling down Wadsworth at 45 miles an hour, or you're on the highway at 65 miles an hour. What would that do to your reaction time? And explain why. And then suppose that you were traveling at a bigger speed. How would your answer to the reaction or the stopping distance change? And explain why. And then question 5 is saying, now you're driving down your neighborhood street at 30 miles an hour, just like we were with the moose, and you're behind another car. And this car in front of you stops suddenly because maybe a little kid runs out into the road chasing a ball. Think about how much distance you need to stop. So you just calculated that. And then think about what happens if you're tailgating 2 meters behind that car. So instead of, however many stopping distances you need or car lengths you need, you're only about 6 feet behind that car. What's going to happen and why? So that is the rest of this moose problem. And stopping distance, a classic. Thank you.